Hey, Dave here. So recently, I asked Claude Sonnet 4.5 to make me a regex engine in JavaScript, implement it in JavaScript, an automata-based regex engine. And it turns out that it made me a faster engine than the native JavaScript regex engine, according to some benchmarks. Now, there's an asterisk there. We're going to get back to the catches to that. But that's what this presentation is about. So, a few caveats before we get started. I am aware of the multiple serious controversies involving AI tools. I'm not doing this experiment to promote AI and be like, just do this. But the real reason for this experiment is I think many engineers, myself included, you may want to check in on us. We're undergoing kind of an identity crisis. And so this particular project, it's an interesting uh, check-in on the state of the technology because it's been out for a few years, but it's still early in the overall history of AI, probably. So it's an interesting check-in on its capabilities to see how far it's come and what it's capable of. Okay, in light of that identity crisis that we're undergoing. And so you could maybe generalize some of these things that we're talking about today, but you should know I'm using a specific AI tool. I'm using Claude Sonnet 4.5, specifically the free chat version of it. And you know what? This is like just an experimental library. If you use it in production, that's your own problem. Okay, so I actually wanted to do this myself, and I set out to writing an ABNF grammar for regex, and I was nearly complete when I thought, I wonder if AI could do this. I was just curious. And so I set out to ask Claude to do it. So I wanted to make an NFA simulation approach. NFA means non-deterministic finite automata. It's a way of solving regular expressions, right? There's multiple ways of solving these. Another popular one is called backtracking. And the native JavaScript regex engine, if I'm not mistaken, is a backtracking engine. I always wanted a a tool in JavaScript similar to RE2, where I could just do a little bit of simple regex, specifically only supporting like the first 256 code points, talking like Latin 1, basically. Um, just something that I could use on strings or even on binary buffers. And why? Well, if you watch my previous videos about adaptive radix trees and things, that might make sense to you. But they're in reality more mature regex libraries. They support advanced features, right? Like matching a broader range of Unicode code points. And not that you couldn't, in theory, use a library like this to match text or language encoded like that. Really, the focus is just simple 256 code points like Latin 1. And like I said, support strings and uint8 arrays. So I want the core regex operators, right? Concatenation, alternation, star, grouping. And I wanted to support some of the common higher order features that are common to most engines. So this means like character classes, right? Quantifiers and capturing. Okay, so that's the kind of regex engine I wanted Claude to make for me. And so I thought about what methods should our NFA regex class support? Well, I wanted to have a test function that returns a Boolean value, true or false, based on whether the um, string or binary buffer that you give it matches the regular expression provided, and that being fully anchored, a fully anchored test, right, from start to end. I wanted a count function, so that will tell you how many matches, by using this regular expression, how many matches can you find in the text, right? So, um, you know, non-overlapping matches. And then a search method, so you can give it a specified index in the string or whatever, and then it'll start searching from there, and then perform a match, and then register an instance property called last index after match. Okay, so it's kind of an unanchored search thing. And then finally, extract and extract all. So these are similar to search, but these would give you capturing, so you can actually capture matches from within the array. And these methods, instead of actually returning the substring like many libraries do, I'm just having it return the indices of the matches associated with each capture. So these are the goals, right? And there are more things that you could want a regex engine to do, but this is what I had them do. And so what were my prompts like? Well, relatively short, a small paragraph or less. I started with a request for an ABNF grammar for regex patterns. Then after that, I had it convert the ABNF grammar to Peggy.js parsing expression grammar. And then after that, I had it write a tree walking routine or interpreter for the Peggy.js abstract syntax tree. And then after that, I made several rounds of asking for new features to be added to the class. And so that's how I did it. I realized there are these, protocols now, and I have used the tools where you have like like you have the one agent like writing the code, and then you have like an architectural review, and then they go back and forth, and they're like arguing a little bit, and things like that to simulate like some kind of a um, multiple engineers kind of a deal. And I'm not, to be honest, I did not have a great experience with those. And so I wanted a project specifically like this where I could have kind of a conversation with it and have it make a not really tiny scope, but a real reasonable scope thing like this. And so, and then after each feature that I have it add to the class, I usually ask for a small round of simple tests or demonstrations for each feature. Okay, and so then let's get to the benchmarks. After completing it, I did some benchmarks. And the background to this, I made prior write-ups and YouTube videos. I made multiple benchmarks with the native JavaScript regex engine out of two large data sets. So that's Moby Dick and the complete works of Shakespeare. So with my adaptive radix tree library, I used it to compile trie-style regex patterns from all the unique words in Moby Dick. And then I did that too with all the unique words in the complete works of Shakespeare. These are massive regex patterns, 116 KB for Moby Dick and 183 kilobytes for the complete works of Shakespeare. Those are really fun. Look at my YouTube channel if you want to watch those experiments and how I did it. But I'm returning to those two data sets to test which engine takes longer to compile the massive patterns. Is that my regex engine that I had AI make me, or is that the native JavaScript regex engine? And the other question is, which engine takes longer to test all the words that comprise the massive patterns? So these are the results of the Moby Dick benchmark. So these are the runtimes, and I did this benchmark on my phone, and I also tested on another device. I got similar results on another device, different runtimes, and a little bit different ratios. Okay, so different devices and different versions of Node, you're going to get different results. But overall, this trend is pretty true. Okay, um, the average runtime I had of out of these 10 runs. Okay, so where each run we're testing each of the words against that massive regex pattern. Average runtime for doing all of that was just over 4 seconds. That's for the NFA library that Claude made me. Then the native JavaScript regex engine, over 26.5 seconds. Okay, so that means that the native JavaScript regex engine for this Moby Dick benchmark, the really large pattern, it took almost 6.5 times as long as the NFA library that JavaScript made me. And that is incredible because the JavaScript regex native implementation is, some kind of lower level, native code that's doing that. Whereas the NFA that Claude made me, it's just literally JavaScript. So that is a wild benchmark result. Then I did the same thing with Shakespeare, and it's less impressive actually. So again, compile the massive regular expression trie-style regex pattern that matches all of the words in complete works of Shakespeare, all the unique words, then iterate through all those unique words and test them against the regex. And the NFA did it in just under 19.5 seconds on Termux on my phone. Native JavaScript regex, almost 31 seconds. And so this is just a little more than 1.5 times as long. Okay, so not as incredible as the Moby Dick benchmark, but still slower, right? And so we have this discrepancy with this ratio, right? 6 versus like 1.5 or whatever it is. So let's interpret the benchmarks a little bit. So technically, the compilation of native JavaScript regex is faster than the speed of compiling the Epsilon-NFA. And what that means is that in Termux on my phone, a typical compilation time Okay, and this means the time that the compilation function actually returns and gives you a usable regex object. That compilation time for the native JavaScript regex is usually in single-digit milliseconds, like 7 to 8 milliseconds is a common runtime that I see for these massive patterns. But with the NFA, because we're compiling it in JavaScript, to JavaScript, that is usually like 300 to 400 milliseconds. Okay, so much slower. But that's not the end of the story. Okay, because with these extra large patterns, the native JavaScript backtracking based engine experiences always, without fail, in the first or second execution. Usually, I think it's the second execution. Okay, that means the second word that you're testing. Some sort of excessive execution time anomaly. It always happens in that last several seconds or longer. And my guess is because it maybe even double-digit milliseconds. You'll see in the demo after this. But my guess is what's happening is because it's a backtracking engine, when you use the regex object that it returns a second time, it's like, okay, hold up. This might be used more than once. We're going to go and try to do some type of optimization. Maybe it's doing caching, whatever it's doing. But whatever that optimization or whatever that anomaly is, it's extremely long with the native JavaScript regex engine, and it's blowing these tests out of the water. Okay. The compiled NFA implementation is that it's faster than the native engine in these tests is astounding, but it's just because it's not experience. It's probably just because it's not experiencing that anomaly, right? The performance is consistent. Okay, and so let's talk about what that means, the consistency. So if you look at the NFA Moby Dick versus Shakespeare, the runtime for Shakespeare was for the NFA was almost 19 and a half seconds. It was just over 4 seconds for Moby Dick. And so that ratio comes to about 4.7. And how many words are we testing in Shakespeare? Well, it's over 973,000 versus only just 210,000 or so for Moby Dick. And that ratio is 4.63, which is awfully close to 4.7. And so we know that with the NFA, the performance is predictable. The performance is pretty much determined by the number of tests that you're doing, and none of them are anomalous. They have predictable runtimes. The native JavaScript, regex Moby Dick versus Shakespeare, that ratio doesn't hold at all. Okay, the time ratio difference between the two is 1.16. Okay, even though it's 4.6 times the number of tests. And so this means the time taken in the NFA, it scales linearly with the number of tests. And due to the excessive optimization time anomaly in the second test of the native solution, the same is not necessarily true. But in my opinion, it does mean that probably the typical runtime, okay, probably the typical runtime, not the anomalous runtime, but just the other runtimes, the typical runtime for an individual test is probably still faster with the native JavaScript regex engine. Okay. But as you'll see, that anomaly, it's a big anomaly. And that's going to lock it. If you do that on a website in your main thread or something, that's going to block your main thread for an unusual amount of time. So in my opinion, it can be kind of a deal breaker depending on what you're going to use this technology for. And so another question is, how hard of a test is this for Claude Sonnet 4.5? Well, Thompson's construction is the famous algorithm that's used for this, for compiling regular expressions to non-deterministic finite automata. It's an algorithm developed by one of the most famous computer science greats who won some of the highest awards in the field, right? Ken Thompson. So this is not a trivial algorithm, right? This is a huge historic thing. On the other hand, this technique has been around a long time. It wasn't discovered yesterday, it was discovered a long time ago, so it's implemented and discussed plenty of times. So I would consider the amount of hand-holding that I did with Claude to get this outcome, maybe only slightly more than minimal. This was accomplished in less than a day or so across about 18 prompts in one chat. Okay. And Claude was able to do this. So that to me is pretty incredible. Okay, now we're going to shift over to the demo. Okay, so here we are in the project directory on Termux on my phone. This is the same device that we did the that I actually collected the benchmarks on. So this is the actual project directory. So I'm just going to show you. Okay, this is the library. And you can look into it more. I'm not going to go any further than that, but that's what's being used. Okay, that's the library that it generated. So at this time, I'm going to go back into the adaptive Regex tree project directory and to its benchmarks, because this is where the benchmark scripts for this related to Moby Dick and Shakespeare are. The reason for that is that actually we did a lot of prior benchmarks with Shakespeare and Moby Dick with the adaptive Regex tree project, so that's why it's in this project. And when I'm using Rex-NFA, I'm just referencing and importing it right from, I'm reaching out into the neighboring directory. So first I'm going to show you a glimpse of what the regex patterns look like. These are the massive prefix or trie-style regex patterns. Okay, that's the Moby Dick one. Okay, and that's the Shakespeare one. Okay, so at this time, what I'm going to do is I'm going to show you actually, let's take a peek inside the script. So this is the script where we're compiling the Moby, we tokenize the text of Moby Dick into individual words, then we insert them into the Regex tree, then we compile regular expressions, and then finally we take the compiled regular expression and make a JavaScript regex object, and then we iterate through all the words, and we test them in the regex pattern, and we print out, the number, the index of the word, and whether or not the test was successful. Okay. And so that's how the test script is working, and you can see we're using the native JavaScript regex for this one. So I'm going to run this just so you can see the anomaly, the performance anomaly that I'm talking about with a native JavaScript regex engine. Okay, so there you can see we're on the second word. Okay, so just speaking informally, I would say that was I'm guessing maybe 13 seconds, okay, just for that second test, and it does that every time. Also on the second test in the Shakespeare version, it also does that. So I'll show you the Shakespeare version. Okay, and this isn't actually the real performance test. There's a separate one that I'm using for collecting the performance numbers, because obviously in this test that I just showed you, we're taking time to print out each of the individual lines, and we don't want to, factor in that time. Okay, so let me now show you the Shakespeare version, and this will also show you the same anomaly that I'm talking about during the second test, that long execution time anomaly. Okay, so that was about 26 or 27 seconds for that second test case. So these performance anomalies are very severe. They will lock up your website if you're using a large regex pattern like this, and you're not doing it in like a background thread or something. Okay, so I just wanted to be real with you. They do that. Now let's go and do the actual hold on a second here. Let's look at what we have here. Yeah, so the one that does the native engine that does not print the, my bad. Oopsies, my mistake. That does not print out each of the tests so we can get a proper sense of how long it actually takes. Okay, so there you have it. Between over 16.5 seconds there you can see. You can see the compilation duration was only less than 7 milliseconds, 6.8 milliseconds. So that was really fast. But again, that long performance anomaly, and we're looking at, 16.5 seconds or so for Moby Dick. Okay. And if we think that maybe, I don't know what it actually was, 10 seconds, you see a huge chunk of that is the performance anomaly. So let's do I'm going to show you now I think that's what it's called, NFA, Regex, NFA. There we go. So this one, you can see, look, it just jumps right into all of the tests, and it never encounters a performance anomaly with the NFA-based approach. It does take a little bit longer. Okay, I think the typical case takes a little bit longer. Overall, the test is shorter because it's missing that performance anomaly. And let's actually, I think, is this the one? Yeah, this is the one that does the test without printing out each individual test. And look at that, less than 4 seconds. Compilation duration, 359 milliseconds. But the test duration, less than 4 seconds, right? So we're definitely beating the native engine here, okay? And just for the sake of completeness, I'll show you the, my bad. I'll show you the Shakespeare one as well. So we have, I don't remember which one is which. I guess we'll find out. There we go. This one's going to go on for a long time. But that's all I wanted to show you. That performance anomaly associated with the native engine is the killer, right? It's the thing that makes the prospect of even using it unusual. If I was using this on a website in a browser, the only way that I could see doing it would be to put it in a web worker, and even then, I'm not sure with some of these execution times with that anomaly, it's almost like, you have to manually test a few times, test the pattern a few times just to make it past that anomaly and somehow schedule that, in a web worker. I don't know what you would do. If it's on a server, that's a big problem. You wouldn't want to do this on a server, like an API server, which is sensitive to latency, because then, if your typical return time for your API calls is at like milliseconds, and all of a sudden, you're 20 plus seconds, right? That's not a good look. So I do believe, based on these tests, that actually the typical runtime of the typical test, not the anomalous one, the typical test is faster, with the native engine compared to the JavaScript NFA, but that anomaly is a deal breaker. So thanks for watching.